Hello, everyone, and welcome to another wonderful day of PChem. So today we're going to be starting by picking up where we left off by taking our hydrogenic Hamiltonian and figuring out how we can split up our Hamiltonian and our wave function into a little bit more manageable parts. So last time we took our kinetic energy portion of our Hamiltonian and we split it up using the Legendrian, splitting it up into a series of radial components and this little pesky bit of the Legendrian over r squared. In addition, we also have this extra potential term, which represents the attractive nature of the nuclei to the surrounding electrons. However, one of the first things we're going to want to do is try and pull out the Legendrian because it's going to it's our only term that depends upon the angular position of the electron. And again, this is going to be the only thing that gives us kind of the angular shape of the system. So we can then go ahead and pull this out front. And so now I've identified all of my angular contributions in this single part. So the rest of this now just becomes a radial Hamiltonian. Now, because we're able to separate our wave function in terms of radial and a little bit of angular components, this means that we should also be able to separate out our wave function into a radial wave function and an angular wave function. So our real trick is going to be trying to figure out what the forms of these two functions should look like. And the real hint actually is in this term of our Legendrian, because it turns out that since this is our only angular component, all I need to do is find a set of functions that are going to be eigenfunctions of the Legendrian. Well, it turns out we've done that already, because the Legendrian showed up when we did a rigid rotor, where essentially we set all of these terms, all of our other kinetic terms equal to 0, and we were just left with this component. And if you remember, our solutions for the Legendrian were our good old friend, the spherical harmonics. So it turns out the spherical harmonics are back because they're going to be our sole expression of angular position of an electron around a nuclei, which might be one of the reasons why they looked familiar in the past. And so all of our angular portions of the wave function can be given by these spherical harmonics. So let's do just a quick review of our spherical harmonics. So as a quick note, our angular distributions and the spherical harmonics are controlled by two different quantum numbers. The first one being L, which is going to give information about the total angular momentum, how fast and how directional is the movement about the nuclei. 0 means it's essentially ambling about, and we'll find an even probability distribution at all points. The faster it moves, the more localized the path is around the nuclei. However, it turns out that this isn't quite enough, because as soon as I start generating this angular momentum, I'm presented with a second question, which is, in what direction is that angular momentum pointed? And we essentially have three choices. It can be pointed essentially somewhere away from the z-axis, or it can be pointed up or down. And so if L is 0, we have essentially angular momentum pointed up, or be pointed towards the xy plane. +1, it's pointed up. -1, it's pointed down. So in this cases, it's more or less moving in a ring up and down. In this case, it's moving, in the plus case, it's moving clockwise. In the negative case, counterclockwise. And of course, this gets amped up as we get the higher and higher angular momentums, where the direction can now be not just up, down, or in the x-axis, but also somewhere in the middle, because I have more options for angular momentum. And so, not too surprisingly, these spherical harmonics are really going to become a major feature of building our atomic orbitals, as they're going to give us the classic shapes that define s, p, and d orbitals. And we're going to devote several whole lectures on these. However, for the meantime, one of the most important parts about using these spherical harmonics is that when I apply the Legendrian to these spherical harmonics, it gives us a known set of eigenvalues, with the eigenvalues being, if you may remember, just dependent on the total angular momentum. They don't depend on the direction of the angular momentum, just how much of it I have. So our eigenvalues are simply going to be L times L plus 1. Now, one of the reasons why this is actually kind of cool is because this gives me a modified way to express my radial Hamiltonian. Because what I can do is I can put these solutions of my eigenvalues into my general Hamiltonian and essentially introduce, instead of a single monolithic radial Hamiltonian, a series of radial Hamiltonians that have different forms depending on the total angular momentum. As I'll have the kinetic energy of the Hamiltonian, which should in net be negative. And again, another attractive component here, as the nuclei is attracted towards the electron is attracted toward the nuclei. But I'm also going to have this fun repulsive component, as higher angular momentum is going to push the electron further out. Now that we have essentially a set expression for a radial Hamiltonian, again, as a function of our total angular momentum, again, with no dependence on shape, we're going to next time develop these radial distributions, as I can get a set of eigenfunctions and eigenvalues to go with this operator. Till then, take care.